This presentation is about graph-based audio synthesis in Rust. With this system, I'm trying to emulate existing hardware called modular unit generators. Unit generators are little boxes that will generate audio sources, and they can feed them into each other or provide different effects. They can take different parameters, which is all the knobs that you see, and they can be fed into each other using the wires. You can combine unit generators together. So you can combine signals using additive synthesis, where say you can combine two notes like a C, E, and G to make a major chord. Or you can use FM synthesis, where you use a sine wave to modulate the pitch of another sine wave, creating a vibrato effect. With this project, I had a few design priorities, which also reflected the things that I wanted to learn. I wanted the system to be node-based. So to do so, I had to implement a graph system. Each component represents a unit generator. So it has inputs and it has one or more outputs. And these can all be fed into each other in the graph. When evaluating the graph, each tick to provide the audio output in that moment in time, I wanted it to be very fast. And to do so, I implemented something called memoization, where to prevent redundant computation, we cache values. I also wanted there to be a very efficient memory management system. So for automatic memory cleanup, I implemented a partial garbage collector, and then I also took advantage of other features within the Rust language of memory management. In order to make this performant overall, I wanted to make sure that the language that I chose was the best one for the task. I didn't want it to be an interpreted language like Java or Python, and I wanted it to also be memory and type safe, so I chose Rust. The graph system is composed of 4 primary elements. Links will hold data within the system. This data can be Boolean values, floating point numbers, vectors, etc. Parameters will supply constant data or retrieve links dynamically from other components. Components will accept parameters and then generate links, which they can feed forward to other components in the network, or provide as the output of the network as a whole. The graph keeps track of all components and will evaluate the network. The example that you see below is a graph-based vibrato synthesis system. We supply a couple of constant parameters to the sine wave component, and then a separate pitch oscillator component will be fed into the pitch modulation of the sine wave. Memoization is a technique commonly used in graph-based systems to prevent redundant computation. Take, for example, the system that we have on the right. We have a single volume controller that controls the volume of 2 sine waves. What if we wanted to use this, but we didn't want to have to recompute whatever function we're using to generate the output volume every tick? Say that we had 1,000 sine waves that we were trying to control, and we didn't want to have to reevaluate the function within the volume controller every tick. What we do is we just keep track of the current cycle that we're processing, and then cache the value of the amplitude output within the volume controller. Consequently, for each subsequent param fetch of the amplitude link, we can return early and just give away the cached value instead of recomputing the whole function. So this is a reusable component in the network. In terms of memory management, I combined together a few memory management techniques. The graph itself I implemented with a partial garbage collector. I wanted to avoid garbage collection initially, but I realized that it would just be easier to implement it myself because the system is set up in such a way that a user would hypothetically be able to disconnect and reconnect components at runtime, and I would have to make sure that all of the components are cleaned up. If a user disconnects a component entirely from the graph and deletes it, I want to make sure that I can run a function that will go through the graph, detect these unused components, and free them automatically. So I wrote a function to do that, and I also used a structure in Rust called an ARC, an atomic reference counter. An atomic reference counter will automatically free resources once they are no longer being used. So the combination of these techniques allowed it to be relatively performant without having to write too much code myself. Again, there's even more focus on performance with this system. When it comes to language that I picked for this project, I wanted to avoid unnecessary runtime overhead. So I didn't want there to be an extra layer of abstraction that I didn't necessarily need. That led me away from languages like Python and Java, which run in an interpreter. I wanted to minimally re-implement features that I wanted, so garbage collection in this instance, but I also wanted to compile to native binaries. This relates to the next slide, which is where I talk about safety. Ultimately, the combination of all of these design wants led me to Rust. Rust is a great language because it provides you a number of guarantees at compile time. Here I could handle type checking at compilation to be sure that I'm always getting the right values from each parameter. If someone writes their own component and says, hey, I need a floating point number at this specific input, I can be sure that it's going to be handled appropriately, such that if the user connects a Boolean value to that component at that input, it won't work properly. I'm also trying to prevent race conditions, for example with link outputs. Say that we're in a multi-threaded environment and we have a couple of components that are trying to read from the same link at the same time. That's fine. So I used a read-write lock. Say that a component is trying to update its output at the same time another component is trying to read from that output. That is not okay. That can lead to a race condition in which the two components are racing to the same source, and one is trying to modify it while the other is trying to read from it. So to prevent this, we use an atomic read-write lock in which only one physical thread on the CPU can access the resource at a time. Buffer reads and writes are also checked at runtime in Rust. So if I'm reading and writing to the audio output, I can be certain that I'm reading and writing to the correct positions in the buffer, which isn't guaranteed with languages like C and C++. Finally, I was thinking more about what I would want for next steps with this project. I think I might implement a command line interface or a graphical user interface in which the user could drag and drop components onto a surface and then connect them together using wires, almost re-implementing what the real world looks like in a display. If I did this, then I would also have to rework the error handling system so that I can forward up errors from the graph over to the user interface. Say, for example, that a user connects a Boolean output to a floating point input. That wouldn't be okay, so I would have to propagate an error up out of the graph system into user land. I would also want to add additional components. For example, a square wave output, a compressor effect, a distortion effect, or more. Let's get to a real-time demo of this project. Here I'm showing you my codebase, and I'm about to play an effect for you that I created. When I play it, I want you to keep a couple of things in mind. First, it's generating a sine wave, but second and more importantly, it's parameterizing the output volume of the sine wave by adding another component in between the sine wave output and the output to the graph. This is an envelope that will reset every couple of seconds. Alright, thank you for watching.